All right, let's get started. Okay, so we're gonna go over 9.2. I don't know what else we'll go over. We're just winging it until we get into class. So last section, we talked about a z-test for testing the difference between two means of independent samples. So the natural thing to do next is to do a t-test for the difference between the two means of independent samples. And then the next section we will look at when it's dependent samples instead of independent. So if the population standard deviations are unknown, then we must estimate them using the sample standard deviations for each group S1 and S2. Because of this, we must run a t-test. So remember, when we don't know sigma, we use a t-test. And then the assumptions that must be made for the test to occur are the first, those samples are random. The second, the populations are normally distributed, or each of the sample sizes is greater than or equal to 30. And the final one, the samples must be independent of each other again. In the next section, like I said, we'll look at what happens when they're dependent of each other. And it's actually a little easier than this part. So then it talks about the two different options that you could actually have for an independent t-test. So one of them is assuming that both of the variances of the population are equal. So assuming sigma 1 squared equals sigma 2 squared. So this is when you assume equal variances for the population. In this case, we're not going to cover it in this class. The formula, it gets kind of gross. The weird thing is they make me cover it in the other class I've taught, which is a lower level class than this. I don't know why. So one option was to assume they're equal. The other one is naturally to assume they're what? Not equal, right? Assuming sigma 1 squared does not equal sigma 2 squared. And this is the one we will look at. So it goes through what each of the options actually is. So the first one, when you assume the variances are equal, this is what's called a pooled t-test. So we're pooling from one group to the next, basically the standard deviations together in something that's called the pooled standard deviation. And that's what's used in the calculation whenever you're calculating a test statistic. We're not going to cover it in this class, so you don't have to worry about it. And on the next page, this is the little summary chart that we give for each of the tests we're doing. And it's basically the same as what it was for chapter 8 when we did a t-test. It's just the null and alternative hypotheses are changing and the test statistic formula is changing. So on the left-hand side, we have for a right-tailed test, the alternative is greater than. So you can write that two different ways. I don't know why it's written twice on here, but the other way you can write this. So let's say mu1 is greater than mu2 is another way to write this first alternative for a right-tailed test. For a left-tailed test, another way you can write it is mu1 is less than mu2. And the final one is mu1 does not equal mu2. So those are the other type of ways you can write the alternatives. And then it gives you the decision rules like it has for every test that we've done. So for a right-tailed test, you reject if you get a test statistic greater than the critical value. For a left-tailed test, you reject if it's less than the critical value. If it's right-tailed, you do either or. So the easiest way to say it is reject the null hypothesis if the absolute value of the test statistic is greater than the positive critical value. Then again, the p-value approach is always the same decision rule. Reject if you get a p-value less than or equal to alpha. And then the confidence interval method only applies to two-tailed test. And you reject if the confidence interval does not contain 0. Because if you look up here, the null value is 0, right? If we at least write it as a difference between the two means. So the test statistic is pretty similar to the one we had in the last section when we did a z-test. The only thing that changes is you don't know the population standard deviations, so you have to use the sample standard deviations. So the test statistic t-test becomes, in the numerator we have x1 bar minus x2 bar. And last time, remember, I put this minus mu1 minus mu2 here as well. And then we divided by the square root of S1 squared over N1 plus S2 squared over N2. But remember, what piece goes away and makes that formula a little simpler? Yeah, mu1 minus mu2, because under the null hypothesis of each of these, mu1 minus mu2 is equal to 0. So that means this here goes away. So this is 0 under HO again. So it just reduces to x1 bar minus x2 bar divided by that same denominator. The square root of S1 squared over N1 plus S2 squared over N2. And that's the final test statistic form. Not much change. Do you think much changes in the confidence interval? No, it has the same pattern, right? I'm going to have the numerator x1 bar minus x2 bar. That'll be the point estimate of mu1 minus mu2. So I'm going to have x1 bar minus x2 bar plus or minus a critical t value, since we're doing a t-test, right? Critical t value times the denominator. So in most of these scenarios, whenever we're calculating the confidence interval, you can actually look at the test statistic, and most of the stuff that you're going to use in the confidence interval comes from it. So here you have the numerator plus or minus a critical t times the denominator. There's one instance where this doesn't happen, and it's the last section of this chapter. So this is times the square root of S1 squared over N1 plus S2 squared over N2. So that's the confidence interval formula that we're going to use. Let me move that down a little bit. There you go. So recall from chapters 7 and 8. Whenever you went to find a critical t value, you had to use what to find it? Anyone remember? Yeah, you had to use the table, but what did you have to look at on the table? On the left-hand side, there was a what?
Degrees of freedom.
Degrees of freedom, right? You needed n-1. Now what happens? There's two samples, right? So there's a different way we calculate the degrees of freedom. We'll talk about it here. So there is a formula that is actually used by your calculator to do this. So the formula that your calculator uses is this. It's pretty gross, so I'm going to write it out. So the degrees of freedom ends up looking like this. So in the numerator, we have S1 squared over N1 plus S2 squared over N2. And then in the denominator, we have S1 squared over N1. So this is S1 squared over N1. This quantity squared divided by N1 minus 1. And now what do you think I do to that? I add to that the same thing where I deal with S2 and N2, right? So this would be S2 squared over N2, this quantity squared, divided by N2 minus 1. Everyone okay with that? That's disgusting, right? Yeah. Are we going to use that? Do you want to use that? The answer is obviously what? No, you don't. So there's an easier way we do it. So the formula I just wrote up there is referred to as the Satterthwaite's approximation for the degrees of freedom. So this is the one test we will do in this class that you can't do on the calculator, because it uses a different degrees of freedom than what our textbook does. So we're not going to use that formula. So using that idea of previously we used n-1 to be the degrees of freedom, right? So we're going to use that idea here in a different way. So the sample sizes for each of the groups don't have to be the same. They weren't in the previous section for all of them. So the way we find the degrees of freedom in this section is this. You take the smaller value between n1 minus 1 and n2 minus. So think of it this way. We're looking at the degrees of freedom of each of them as if it's a one sample t-test, and then we're taking the smaller of the two. Then it becomes a little easier than dealing with that disgusting formula left, right? Is everyone okay with that? Okay. Now, I'm going to do the same thing I did last time. We're going to go through one test, and we're going to use all three approaches to do it, at least if it's two-tailed and it ends up being two-tailed. So let's look at it real quick. Does everyone have the stuff on this page? There was the disgusting formula, the Satterthwaite, and then the rule you use. Right. Let's look at the example for this section. So it's talking about comparing birth weights of newborn male and female infants. So it says a researcher wishes to see if the average weight of newborn male infants is different from that of newborn female infants. She selects a random sample of 10 male infants with a mean weight of 123 ounces with a standard deviation of 8 ounces. She selects 8 female infants and finds that their mean weight is 116 ounces with a standard deviation of 5 ounces. Can it be concluded at the 5% significance level that the mean weight of the males is different from that of the females? So the null and alternative hypothesis, we don't really need any of those numbers in there. We just need, first, for the null hypothesis, remember that the null hypothesis for each of the ones in this section and the past one is mu1 minus mu2 equals what? 0, right? Or we can say the two group means the same. U1 equals mu2 is the other way to write it. So that's the other way to write it. So now, what do you think the alternative is? Yeah, not equal, right? It says, are they different? It doesn't indicate whether the difference will be in what direction, so it's just not equal to. So one way of writing it would be mu1 minus mu2 does not equal 0. Or you can say that mu1 does not equal mu2. That's another way to write the alternative. So that's the null and the alternative. Now, which one is the claim and which one's not the claim? Alternative is the claim, right? Can it be concluded at the 5% significance level that the mean weight of the males is different from that of the females? So this is the claim, the alternative. The null is not the claim. And again, it's a two-tailed test because the alternative is not equal to. So now is to where the part where we have to utilize that idea of the degrees of freedom calculation on the last page. Sorry, I'm trying to find the distribution table. There it is. All right. So first we need to find the critical value. So we need to look at what is the degrees of freedom we're going to use, right? So based off the last page, remember the degrees of freedom we use is equal to, we can say the minimum of N1 minus 1 and N2 minus 1. So all we do is plug in N1 and N2. How many male infants were part of the sample? How many? 10, right? So N1 is 10. So this is going to be the minimum between, what's 10 minus 1? 9, right? The minimum between 9. And we had how many female infants? 8, right? So 8 minus 1 is 7. So we're looking at the minimum or the smaller value between 9 and 7. And obviously it's what? 7, right? So the degrees of freedom we use for the critical value is 7. And now, if we want to figure out what the critical value actually is, then you have to go to your table, the t-distribution table. So here is a two-tailed alpha, and alpha is what? What do you think? 0.0. Yeah, the 5% significance level. So alpha is 0.05, and we're looking at two tails. So we're going 7 degrees of freedom. Alpha is 0.05 two tails. So if I go 7, this ends up being what? You can't really see it there. It's 2.365. That's what it ends up being. So the critical value T alpha over 2 is 2.365. So T alpha over 2 ends up being 2.365. So that's the critical value. And since there's the positive and the negative, you can throw the positive and the negative sign out front if you want. So let me scoot this equal sign over a little bit. There. Now you have both of the critical values. And now is where you state your decision rule. So I said that I used 3 different approaches to do it last time. So we're going to do the same here. So let's do the traditional or critical value decision rule first. So trad decision rule is the one that involves the critical value. So since it's a two-tailed test, our decision rule will be reject HO if the absolute value of the t-test statistic you compute is greater than the positive critical value, so greater than 2.365, right? So that is using the traditional method, the decision rule. So it involves the critical value. The next approach, remember, is the p-value approach. So let's say the p-value decision rule then. So remember, the decision rule is always reject HO. If the p-value is less than or equal to alpha. And we said alpha in this case was 0.05, right? So it'd say reject HO if the p-value is less than or equal to 0.05. And then the final way we could do this is using a confidence interval, right? So if I want to do a confidence interval, so I'd say CI decision rule. Then that one is reject HO. If the 95% CI confidence interval for mu1 minus mu2 does not contain 0. So that's the decision rule for each of the 3 approaches that we'll look at. Is everyone okay with that? So now the next step is to compute the test statistic and the p-value and do the confidence interval. So first we want to identify the numbers that we're working with. So x1 bar, do you think is what number up here? So if I zoom out just a tad, x1 bar corresponds to the mean weight of the male infants. And what was that in ounces? 123, right? So x1 bar is 123. Then what is x2 bar for the female infants? Yeah, 116, right? What's the standard deviation for the male infants? 8, right? So S1 is 8. What's the standard deviation for the female infants? S2. 5. What's the number of male infants we had? We had 10, right? So N1 is 10. And N2 is what? 8, right? So now we're just going to plug and chug into the formula. So I'll first write in the formula and then plug everything in. So t-test is x1 bar minus x2 bar. Divided by the square root of S1 squared over N1 plus S2 squared over N2. And now we just plug and chug the numbers from here into here. So if I do that, in the numerator I have 123 minus 116. In the denominator I have the square root of 8 squared over 10 plus 5 squared over 8. When I do that calculation to how many decimal? 2 decimal places, what do I get?
The 2 decimal places?
Yeah, 2.
2.27.
That's correct. 2.27. When you're doing your homework, you can use that Desmos tool I talked to you or showed you last time. That one's easy to do. But I would recommend learning how to do it on your calculator. All you do, I'll just show you real quick. So if you want to do that disgusting thing in your calculator, this is the way you do it. So hit alpha y equals, this brings up this option. You're going to hit n over d. That means numerator over denominator. It's a fraction. Then in the top, just type what you want in the top. 123 minus 116. Now in the denominator, there's a square root, right? So I'm going to hit second x squared right here. Because look, the second here is blue. And this right here is where I see a square root. Now again, hit alpha y equals and select that n over d option again. That gives you another fraction. Plug in what you want there. 8 squared over 10. When you scroll over and you hit plus, do the same thing again. Alpha y equals, select the first option, n over d. 5 squared over 8. There you go. 2.268, or to 2 decimal places, 2.27. Your homework will probably want to 3. Usually with t values, it pretty much wants t, at least 2 or 3, usually 3. Everyone okay with how I did that? What you do, alpha y equals, the first option will give you a fraction. So we figured out what the test statistic is. It's 2.27. Now remember, to find the p-value, it's a little bit more difficult for a t-test. So the degrees of freedom we used to find the critical value was 7, right? So I want to go to 7 degrees of freedom on here, on this little chart. And I want to look at what two critical values does 2.27 fall between. So if I'm going here to 7, 2.27 falls between 1.895 and 2.365. So then that means it falls between these two alpha values. But remember, this is a two-tailed test. So I go up here. So that means the p-value is between 0.05 and 0.10. Everyone see what I did there? First, I went to the degrees of freedom row. I looked at what two critical values does my test statistic fall between. Then, since it's a two-tailed test, I went to the two-tailed alpha up here and looked at what are the values of alpha for two tails that my test statistic falls between those two critical values. So the p-value is between 0.05 and 0.10. So the way I would write that is 0.05 to 0.10. So the p-value is in between those two. You can find the exact p-value on the calculator, but it would be kind of complicated. All right, now let's figure out how to do the confidence interval. So all we do is plug and chug into the formula, right? So let's write it out. X1 bar minus X2 bar plus or minus the critical t-value times the square root of S1 squared over N1 plus S2 squared over N2. So let's plug and chug. So if I plug everything in, that's 123 minus 116 plus or minus 2.365 times the square root of 8 squared over 10 plus 5 squared over 8. So if I do that, I'm going to write out first what this is on the left-hand side. 123 minus 116 is 7, right? So this is 7 plus or minus. I'm going to calculate the right-hand side, the 2.365 times that piece. So 2.365 times the square root of 8 squared over 10 plus 5 squared over 8. It's 7.299. So let's just say 7.30. Let's just yes. So now let's find the limits of this. So 7 minus 7.30 gives you minus 0.3. So the lower limit is negative 0.3. The upper limit, when I take 7 plus 7.30, I'll get 14.30. So 14.3 is the upper limit, right? So now using any of these decision rules and any of those methods we just did, let's look. So is the absolute value of 2.27 greater than 2.365? Yes or no? No. So fail to reject using the first decision rule. Is the p-value less than or equal to 0.05? If you look here, it's between 0.05 and 0.10. So no, it's not less than 0.05. It's actually greater than it. And the last one, it is 0 inside this interval. It's negative to positive, so yes, 0 must be inside there. So using all three of these, that means your decision is what? Fail to reject, right? Fail to reject using any of the three methods. Using any of the decision rules. Thus, there is not enough evidence to support the claim that the mean weight of male and female infants are different. And that's how you write it up. Is everyone okay with that? Did everyone follow along with that one? Okay. These examples take a good chunk of time. All right. So someone emailed me asking when our test would be. The answer is, I have no clue. It won't be next Friday, I'll tell you that. It may be the following Monday or Wednesday after that. We only have 2 more sections left in this chapter. One that looks at a dependent samples t-test, and it actually looks like a 1 sample test from chapter 8. Then the last one is the hardest section of the course, and it's a z-test with the difference between the 2 proportions. The reason it's harder is because it just looks more complicated. Because it involves the pooled proportion, which looks a little bit different than what we saw in chapter 8. But we'll stop there. If y'all are going to the concert tonight or over the weekend, stay safe. Y'all have a good one.